Hello everyone. Welcome to this training session on interest rates. As a part of this session, we will try to cover the different forms of interest rates. We have looked at we have looked at what is the nominal interest rate. We can look at the effective. Effective we have looked at earlier also for that particular month, for that particular year, what is that effective rate. So we'll use these two words, nominal and effective, both in terms of interest rates as well as discount rates. And because some financial instruments are quoted in the form of nominal, some of them are quoted with respect to effective, or in some cases we may see that they are using the interest rates, and in some cases they are using the discount rates. So we should be comfortable in converting the rates from one form to the other. So we have to see whether the interest rate is a nominal rate or a effective rate, or given a nominal rate, how do I convert it into an effective rate? All these kinds of conversions we need to be comfortable with. And along with that, we also will introduce what is called as a continuously compounded interest rate. So which is typically called as force of interest. We'll come back to that again. That's a continuously compounded interest rate. We'll look at even that aspect. So packaging all these things is what we are going to cover as a part of this particular session. So if at all I have to identify the difference between an effective rate and a nominal rate, first thing I would like to bring out, if at all the number of periods is equal to 1, effective rate is always equal to nominal rate. I'm not saying number of years equal to 1. Number of periods equal to 1, I'm making a statement that effective rate is equal to nominal rate. What do I mean by that? If at all I'm talking about a monthly interest rate, monthly effective rate M, and monthly nominal rate is also M. If I'm talking about only 1 month period, the monthly nominal rate will be the same as monthly effective rate also. Whereas if there are differences, for example, if I say the annual effective rate of interest is some I, whereas annual nominal rate of interest is some IP. On a nominal terms, let's say the interest rate is IP per year and I is the annual. Typically, if I'm trying to find out the annual itself, right, what is the relationship directly between an annual interest rate and the annual effective and annual nominal, provided the compounding happens annually. If that is the case, then I is always equal to IP. If the compounding happens annually, there is no difference between an effective annual rate and a nominal annual rate. But the problem comes when the compounding happens non-annual, because most of the quotations will be based on the nominal rate. If someone says 8% per annum, see, this is the scenario where you will use that. 8% per annum is the quoted rate, but compounded quarterly or compounded monthly. If that's the case, what is the effective annual rate? So 8% is not the effective annual rate. It's a nominal annual rate, which is compounded quarterly. In this case, I can take the quarterly rate directly as 2%. If this is the kind of an example given, if someone has given 8% per annum effective, then it's not 2% per quarter. You have to really understand the difference here. 8% per annum effective need not work out to 2% per quarter, but 8% per annum nominal compounded quarterly will definitely work out to 2% per quarter. So that is what is the terminology difference, because some banks, most of the banks, the way they quote on their deposits is primarily the nominal rate along with the compounding frequency. So the simple logic always is, if at all I have to find a relationship between the two, first I will take, depending on what is their compounding frequency. So the effective annual rate, we know it is 1 plus I. That I will equate it to, I know that the nominal interest rate is IP. Identify what is the compounding frequency. So if it is semi-annual, you take P as 2. If it is quarterly, you take P as 4. Because I can find out the quarterly interest rate is nothing but 8% divided by 4. And raise it to the power 4, which is raise it to the power P. This is the relationship between the nominal rate of interest and an effective rate of interest. You have to be very careful in the questions, in the examples, or in the scenarios, depending on whether we are talking about a nominal rate or an effective rate, because there will be some difference in the actual values, and we have to be very careful because we may choose the wrong product in case we don't understand the differences at this layer, right? So wherever the duration works out to be 1, there is no difference between the two. But if the duration is multi-period, this is the kind of relationship that works out between the two. Now, if I have to see a small example, at a nominal rate of interest. So we are talking about 1000. That's not going to come today. The 1000 is going to come after 5 years. And the interest rate in the process is 8% compounded quarterly. So there are two models to solve this. Either, so the discounting factor, whatever I may have to find out, I can do it based on assuming that 8% quarterly is nothing but 8% per annum compounded quarterly is nothing but 2% per quarter, and P take it as number of quarters, which is 20 quarters, and find out the present value, which is nothing but, as per the discounting mechanism, 1000 by 1 plus I, 1 plus 2% to the power 20. Take the, because 2% is the effective quarterly rate. If I'm taking off a quarter, if I'm just looking at it as a quarter, then I can very well take it as 2% per quarter, and I'll take it as 20%, 20 quarters, and do the compounding. So which will work out to me as 1000 divided by 1.02 to the power 20. So some 672.97 is the present value, if I am directly doing through that mechanism. But there is another mechanism. I can convert 8% per annum compounded quarterly into an effective annual rate. How do I find out what is the effective annual rate? 1 plus I is equal to 1 plus 8% by 4 to the power 4, which is nothing but 1.02 to the power 4 minus 1 will become the effective annual rate. Okay, let me find out effective annual rate. 1.02 to the power 4 minus 1, which is giving me 8.24% is the effective annual rate. Now all I can do is effective annual rate to the power 5. So 1000 divided by 1 plus effective annual rate to the power 5 will give me the present value, which is nothing but 672.97. Either I do it in terms of quarters or I do it in terms of years. The only thing is I should be comfortable on the conceptual part. We need to first understand whether the interest rate that is given to us is a nominal rate or an effective rate. If at all it is given as an effective rate, nominal rate, how do I convert it into an effective rate? And based on that, how do I find out the discounting factor? You should not get confused across these words, because the discounting factor always applies based on the effective rate of interest or discount. So if nominal is given, either take it as one single period. If period is one, then the nominal and effective are one and the same, or convert it into effective first and then use the effective rate to find out the discounting factor. So these two things have to be kept in mind for solving any kind of numericals. The same logic holds true for effective rates of discount, nominal versus effective rates of discount also. If someone says this is the discount rate, this is a nominal rate of discount, or probably this is the discount rate compounded quarterly. Now look at this numerical, the same logic holds true. If at all we are talking about an annual rate of discount, we said it is 1 minus D. Whereas when we are talking about the DP being a nominal rate of discount, compounding frequency being P, I can raise it like this. So the same logic, if at all we have 8% compounded quarterly kind of scenario, I want to find out what is the effective annual rate of discount. So this will actually work out to 1 minus D equal to 1 minus 8% by 4 to the power 4. So 1 minus 2%, which is nothing but 0.98, 98% to the power 4, right? So this works out to 0.98 to the power 4, and 1 minus this. So this becomes 1 minus this, which works out to 7.76%. The actual effective rate of discount corresponding to 8% annual discount, 8% nominal rate of discount compounded quarterly is nothing but equivalent to 7.76% effective rate of discount. So we have to be careful building out the relationships here, because any kind of numerical that we come across, different financial products being priced at different rates, we should be comfortable in finding out what is the effective discount rate, what is the effective interest rate. Now let's say we got the effective discount rate as something like this, right? Effective discount rate is something like this. Now if I want to convert this into an effective interest rate, what is the link between the effective discount rate and effective interest rate? We have already seen. V is the linkage. 1 minus D equal to 1 by 1 plus I. Right? So now the D we have got it as 7.76%. So 1 plus I will work out as 1 by 1 minus D. So D is already here. So I'll make it as 1 minus D first. Then I'll make it as 1 by 1 minus D. And that is 1 plus I. So I will work out as this number minus 1. So 7.76% effective rate of discount is nothing but 8.42% effective rate of interest. So this conversions is the most typical aspect. There is a huge difference. 7.76% rate of discount working out to 8.42% effective rate of interest. So we have to be very comfortable in solving the numericals of this kind, because different financial products will be priced differently based on these various notations. Then one more concept which we have to discuss in this particular chapter is the interest rates, instead of being showing a discrete kind of a property, they will show continuous. Why compounded quarterly? Right? We are talking about compounded quarterly, or we are talking about compounded monthly. Now let me reduce it a little bit more. Compounded daily, compounded hourly. Now, like this, if it goes down and down and down, compounded every minute of a second, every millisecond, microsecond. That is what we call as continuous compounding. So a lot of instruments again are priced based on continuous compounding kind of method, no longer annual compounding or quarterly compounding or semi-annual compounding. We always talk about the scenario of continuous compounding. And that continuous compounding rate of interest is what is denoted by delta. Right? That is what actually we call as force of interest. And what we see is, because we are talking about an interest rate between this period to this period, and we are saying that the compounding is happening across this period. So what typically we are bringing out is, again, if the compounding is happening at a very frequent intervals of time, not even quarterly, not even monthly, it's much more frequently than even a daily or even a hourly kind of stuff, we call it as continuous compounding. So I may have to link again these words with I, V and D, because this is one more new concept which we have brought in. This is also another form of interest, because I is effective rate of interest, D is effective rate of discount, and delta is nothing but the constant or probably the force of interest, which is nothing but continuous rate of interest. So again, all these should be linked, and the typical linkage formula is with respect to I, you can work it out, log 1 plus I. So the delta comes out to log 1 plus I. Now let's see all the relationships. Delta comes out to log 1 plus I, and we know 1 plus I is nothing but 1 by V, because V equal to 1 by 1 plus I. So 1 plus I will become 1 by V, and as per the concepts of logarithms, this becomes minus log V. So that is what I'm mentioning here as a second point. Delta, if at all the question contains constant rate of interest, or probably compounded, continuously compounded, because I don't want to use constant, because in some cases even that could be variable also. Continuously compounded rate of interest, we have to take it as delta itself. And that delta can be found out, even if I know the effective annual rate of interest, I can find out what is the corresponding continuously compounded rate of interest using log 1 plus I. That is same as minus log V, and we know that V is nothing but 1 minus D. So it can even become minus log 1 minus D. So even if one of these is given, the other can very well be converted into. So that is one. And here is where I want to bring out this force of interest, or this continuously compounded rate of interest can be constant for the entire period which we are considering. Let's say we are talking about a 5-year period. I am depositing now. I will take something after 5 years. I will withdraw after 5 years. Right? Probably it's a continuously compounded rate of interest, but for the entire 5-year period, it is constant. Those kind of scenarios we'll be observing some of them. So where the force of interest is constant, or you may have scenarios wherein, okay, it is constant between this to this period, and some other number between this to this period, some other between this to this period. That is where we call force of interest being a variable. If it is one single value throughout the entire period, we call force of interest as constant delta. Whereas if it is changing with time, If it is changing with time, we call it as a variable. So we'll look at both. In both of them, I want to know the accumulation factor, which means if I am depositing 1000, where the effective interest rate is 8% for a 5-year period, right? I am depositing 1000 where the effective interest rate is 8%, effective annual rate is 8%, but it is continuously compounded. So if that is the case, I want to find out what is the amount that, what is the continuously compounded rate of interest here, right? Continuously compounded rate of interest. How do I find out? Log 1 plus I. Log 1.08 comes out to be the continuously compounded rate of interest in this case. What is log 1.08 coming out to log 1.08? So the continuously compounded rate of interest is only 7.69. This is what will be equivalent or 7.7. This is what will be equivalent to getting an 8% effective annual rate of return. So if I want to find out how much will be getting after 5 years, I can very well say 1000 into e power delta t, delta n, delta t, whatever. I'm going to get 1469. But if that 8% was a continuously compounded rate, not the annual effective rate, but it's a continuously compounded rate, then I would have got much higher. 8% into 5, which would have given me 1491. Almost on every 1000, I'm getting around 25 bucks extra. So the continuous compound rate actually comes out to be a much bigger. Again, some instruments, they are priced based on a continuous kind of compounding, whereas some of them you see on a discrete or annual, quarterly. So all that you need to do before we actually get into the real crux of numericals, which can be applied in the practical financial world, we need to understand finding out the future value accumulation, how much your total money is going to be accumulated, going with simple interest, compound interest, continuously compounded kind of interest, all these kinds of scenarios. Similarly, the discounting factor, till now we were talking about the discounting factors like 1 by 1 plus I to the power n, right? 1 by 1 plus ni, 1 minus d to the power n, 1 minus nd, and now we are even getting another scenario, e power minus delta n. If delta is a force of interest or a continuously compounded rate of interest, the discounting factor will typically become e power minus delta n. We have to be comfortable on all these kinds of terminologies, jargons, and conversions from one form to the other. Now, one more important thing that we have to focus in this context is if that rate of interest is not a constant, it's a variable. That is what we call as variable force of interest delta. Wherever we come across the variable force of interest, and I want to find out the accumulation factor between some two time periods, because most of the times what we see is the variable force of interest changes with time. So whenever I want to find out the area, the accumulation factor between the time periods T1 and T2, it is suggested that you do an integration of that delta T force of interest between the two timelines. Take your delta T, e power delta T is the accumulation factor. You integrate it between T1 and T2. Because if it is constant for the entire period, we would have integrated it between 0 and infinite, or 0 and t at least. The whole period, it is constant. So what would have happened going with the basic formula itself, e power delta t by delta, the integration part, we will take it as t and 0. So we can get the accumulation factor, typically e power delta t minus 1 by delta. That is what comes out as the accumulation factor in case we are looking at it between 0 and t. It is changing at the same rate. But if it is constant, then across the board, I don't need a separate integration. I have been using it as e power delta t directly. But if at all I am saying that it is constant, it is exhibiting a variability behavior, then the integration is required for e power delta t between t1 and t2. So if there are multiple, like between t1 and t2, it is something. Between t2 and t3, the force of interest is something else. Now, if I want to find out the accumulation factor between t1 and t3, we can add up the two integrations. So T2 to T3, you do another integration wherein probably you are taking minus delta 1 into T dt. So these two integrations you can simply add up. So for that, a small comfort level on integrations is very much required. So if I know the continuous compounded rate of interest is typically a variable and not a constant, and I want to find out the accumulation factor, I'll use the integration like this. If I want to find out the discounting factor, also the same logic will be used. E power minus delta t. Okay, the integration is actually at the power level. E power minus delta t dt between t1 and t2. Right, earlier also the accumulation factor is between e power t, and between t1 and t2 I do an integration of delta t dt. Right, that's where if we had said between 0 to t, we are getting out as e power delta is constant. So we can directly find out between 0 and t. Whereas in this case also I will take e power minus integral between t1 and t2 delta t dt. This is what is the discounting factor, or finding out. This is the formula we have to use for the present value in case the delta is variable, which means generally you will find numericals are typically the scenarios like this. Between 0 to let's say 5 years, the delta t is something like 0.05 plus 0.001 t, whereas when t is greater than 5, delta t equal to 0.07. If this is the kind of case, find out the present value of something or future accumulation value of something. These are the typical kinds of scenarios that come up, which means you do a separate integration from 0 to 5, separate integration from 5 to whatever is the time period of your investment. Use the different values for delta for the different time periods. In some cases, the delta may be constant. In some cases, the delta may be variable, but use it for the different time periods, and you can use them to solve the various numericals. So in this chapter, the prime focus, though we'll look at some of the numericals of this chapter separately, but just to summarize this chapter, the major focus of this particular chapter is discussion between the nominal rates and effective rates, both for interest as well as discount. How do I convert from one form to the other? and there is a discussion on force of interest, which is nothing but the continuously compounded interest rate, which actually can be either constant or variable. So in case of constant, how do I find out the accumulation factor, which is e power delta t, or discounting factor, which is e power minus delta t? In case of variable, how do I find out the accumulation factor, e power integration of t1 to t2 delta t dt, and probably the discounting factor, e power integration of minus t1 to t2 delta t dt. So this is what is a summary of this particular chapter. I hope you got that basic comfort level in terms of understanding the various aspects in this. If you have any further queries regarding this particular session, you can very well get back to me on the numbers that is provided below. And at the same time, you can even send in an email to me at my address, vamsidhar@pacegurus.com, explaining your doubt. I can very well get back to you. Thanks a lot for listening to this session. Thank you very much. Hello, everyone. In this session, let's focus on the numericals more specific to the interest rates. Right? We have looked at the theoretical aspects for interest rates. We will focus on solving a couple of numericals on these things so that we get a comfortable ground in terms of understanding these scenarios, especially the force of interest related problem. Look at this example here. We are talking about a variable force of interest, wherein we are saying that for up to 5 years, 0 to 5, the force of interest per year is going to be something like this. It's a continuously compounded rate of interest, but probably we are seeing that the continuously compounded rate of interest is constant above 5 years at the rate of 5%. Now, my intention is, if at all I'm going to receive 1000 at the end of 17 years from now, going with this kind of expected interest rate patterns, thinking that the interest rate patterns for the next 5 years are going to be something like 0.04 plus 0.02t, which is continuously compounded, and 0.05 continuously compounded after 5 years. So how much should be deposited today, if that is the kind of a requirement? So basically it's finding out the present value, and we have said the discounting factor, probably it is nothing but 1000 into e power minus delta t. But that would have been the case if delta is constant for the entire period, for the entire 17-year period. Probably if delta had been constant, I would have taken it as 17 times whatever is the delta t, probably 0.05 or whatever it is. This is what we would have considered. If it is 5% continuously compounded for the entire 17-year period, this would have directly become the present value. Probably let's see this. If it had been the same 5% across, then the present value would have been 1000 into e power minus 17 times 5%. So typically it would have been something around 427. So if I deposit 427 and I'm getting around 5% per annum, continuously compounded kind of an interest rate, then that would have been boiling down to a total of only 427. That would boil down to 1000 at the end of 17 years. But here, the way we are looking at the interest rates is slightly different. We are saying that between 0 to 5 years, there is some kind of variability in the interest rates. If that is the kind of scenario, then we have to use our concepts of integration. So basically, if at all I want to find out the total present value, right? The way we should approach is I want to find out the present value or a discounting factor for any period greater than 5 years. So how do I find out e power minus integration of between 0 to 5? We know that the interest rates are 0.04 plus 0.02t. Because I am integrating it, I'll use another variable s, ds. And we also know that if at all I'm talking about between 5 and 17, or let me make it more general, between 5 and t. So either I would be multiplying these two or adding at the power level. That's okay. E power 5 to t, whatever is the t, e power minus 5 to t. Let's talk, we can substitute 17 later. This becomes 0.05 ds. Now using this is what is probably I can add up at the exponent level, but keep that aside. So I can very well find out the integrals. Okay, for this part minus I am taking out. So 0.04 will become 0.04 s plus 0.02 into s squared by 2. This entire thing is integrated between 5 and 0. Whereas the next part, which is e power minus 0.05 is a constant, so the integration will lie as 0.05 s, which has to be integrated between t and 5. So this can very well be multiplied, or probably I can add them at the power layer. Fair enough. Now we'll try adding at the power layer. Now substitute 5. So the first part, this part typically simplifies to e power minus, if I substitute 5, it becomes 0.02 plus 0.02 into 5 squared by 12, right? S is 5, sorry, it becomes 0.2, not 0.02, and this becomes 2, so this becomes 0.25, 25 by 2 into 0.02, it becomes 0.25. So the left hand, for the first expression typically becomes a constant, which is e power minus 0.45, which is the discounting factor for the first 5 years. Whereas in the next 5 years, it is working out to 0.05 into t minus 5. Because t is a variable. If I take it as 17, then it becomes 17 minus 5, whatever it is. So on simplification, probably this is coming out to e power minus 0.45 into e power 0.05 t into e power minus 0.25, right? Which is working out to e power 0.05 t e power minus 0.05 t minus 0.2, right? Minus 0.45 into minus 0.05t plus 0.25, which is working out to this. So probably you can very well simplify for any kind of t which is beyond 5 years, the present value is nothing but e to the power of minus 0.05t minus 0.2, or plus 0.2, sorry, e power minus of 0.05t plus 0.2. So given in this numerical, we want for 17 years. So I'll take it as e power minus, I don't need to do integration anymore, 0.05 into t, which is 17, comes out to 0.85 plus 0.2, which works out to e power minus 1.05. So the discount factor in this case is e power minus 1.05. Let's see what it works out to. So the 1000 into e power minus 1.05 will be the solution here, which is nothing but 341. If the interest rate has been constant over constant 5% for over the entire 17-year period, we would have got, we would need to deposit 427 today to become 1000 at the end of 17 years. Whereas if the interest rates were varying as per the model which we have highlighted there, we just need to deposit 349 today or 350 today to typically work it out to 1000 at the end of 17 years. So this is one thing we have to be comfortable with. And look at the next question. So this is a way, once we practice a couple of more numericals, you'll get a lot of hold on it. Look at this. Calculate the rate of interest per annum convertible monthly implied by the above transaction. Let's assume for the 17 years, if I want to find out what is the interest rate convertible monthly, how do I find out what is the interest rate convertible monthly? You can very well find out the quoted rate, right? So what is that? It should come out to whatever is the quoted rate. I'll take it as 1 plus I by I12, because we are talking about monthly compounding, divided by 12 to the power 12. This is an effective annual rate, but we want the effective rate for 17 years, which means I'm taking here to the power 17, which will make it into 17 in the numerator. So the discount factor should work out to this number. Whatever is the discount rate that I'm getting, it should work out to this. So basically it is nothing but 1000 when I divide by this number, it should be equal to 349.93, which means from here I should be able to find out what is that nominal rate of interest compounded monthly, which is equal to this entire deal, which means on a monthly compounding basis, what is the rate of return I'm receiving on this simple investment. So let's work it out. First, for simplification, I can do 1000 by 349 as a first step. Okay, as a first step, I'm doing 1000 by this above number. 2.857 is nothing but the accumulation factor, 1 plus I12 by 12 to the power 12 into 17. So based on this, I can simplify 1 plus I12 by 12, which is nothing but this to the power 1 by 12 into 17. 1 by 12 into 17. Okay, this is working out to 1.005, which is 1 plus I12 by 12 is working out to this. So I12 by 12 becomes 1, this minus 1. So this is I12 by 12. So if I want I12, which is the nominal rate of interest quoted nominal rate of interest annually with a quarter monthly compounding, this works out to around 6.2%. So the simple way is, if at all I had to find out the equivalent of this entire numerical where the interest rates were fluctuating for the first 5 years on a continuously compounded kind of a basis, and after that they are constant on a continuously compounded kind of a basis. And if I have to draw the equality in terms of effective in terms of nominal rate of interest country compounded monthly, it works out to this 6.19%. I hope this part of the numerical is quite comfortable. Now let's look at one more. Instead of saying that you will be receiving 1000, this question is saying we will receive, even the receipts are also 10 into e power 0.01t. We will not receive a constant amount. We will receive 10 into e power 0.01t between 6 and 10. Right? If we are receiving a constant amount, we have taken it as 1000 directly, and we have done 1000 divided by e power whatever is the logic we have got. But here we are not receiving a constant, but we are receiving it a kind of 10 into e power 0.01t, which is a kind of a continuous stream of payment per year. It is going to come out something like this. So here we are not sure what is the amount that we are going to receive, or it's a kind of, it's not a constant amount, and it's not coming out at one single period. Different amounts are coming out at different periods of time between 6 to 10. Per annum you are receiving at the rate of 10 into e power 0.01 into t. If that's the case, they are asking about what is the present value. So in the question, if at all you come across the payment that is received in case of continuous stream rather than a discrete stream like the above numerical, how do you proceed with it? So the first part is the interest rate is, probably if I have to summarize it, the interest rate is continuously compounded and variable, whereas the amount that is received is one time, and the duration is also fixed when you are going to receive. Whereas this numerical, okay, the interest rates are still going to be the same, whatever we have discussed above, but the amount that is going to come out is completely variable. It's not a constant amount, and it changes with every year following a kind of a continuous pattern here also. Right? In these kind of numericals, how do we find out the present value? So now, just like the way we have done earlier, what we can very well do is, earlier what did we do? If I wanted to find out the present value, we said we'll take it as 1000 into e power minus whatever is the t1 to t2, probably 0 to 5, 0 to 5.04 plus, probably let me write it here. So earlier when it was a fixed stream of payment, what did we do? We did 1000 into e power minus 0 to 5.04 plus 0.02 s ds, right? In the power itself, 5 to t, we are talking about 0.05 ds. And this entire thing, when we have simplified earlier, it even has come out to 1000 into e to the power of minus 0.05t plus zero point 0.2. Just you can refer back to the earlier simplification that we have done. Now all I am saying is this 1000 I will replace it with 10 into e power 0.01t, because what we are getting is not 1000 now in this example, but we are getting 10 into e power 0.01t, which is changing with time. So 1000 got replaced with this number, which means simplification wise it has simply become 10 into e to the power of 0.01t into e to the power of minus 0.05t into e to the power of minus zero point 0.2. So it's as such as getting 10 into e to the power of minus zero point 0.2 into e to the power of minus 0.04t. This is what we have got during that period. Okay. So this is what we are going to get at one instant. But what we are saying, this amount is going to come on a continuous basis. It's not a one-time payment. Earlier, the 1000 was a one-time payment. But here, this is not a one-time payment. This is going to come on a continuous basis for us, which means this amount, which is a one-time payment, has to be integrated across the entire period. So what is the integration across the entire period? I'll take it as the integration between 6 to 10. The same numbers, e power minus zero point 0.2 into e power minus 0.04 t. Now this part is a constant, so I'll take it out. 10 into e power minus zero point 0.2, whereas the integration for this is nothing but e to the power of minus 0.04 by minus 0.04 integrated between 10 and 6. So this works out to whatever the constant part is 10 into e to the power of minus 0.2 by minus 0.04. Let me do the simplification there. 10 into e to the power of minus 0.2 divided by minus 0.04. At least that simplification is coming out to minus 204. This number I have to multiply with substituting e power minus 0.04 t here, or s. So if I substitute 10 and 6 in that place, what is coming out? Minus 0.4 minus e power minus 0.4 minus e power minus 0.24. So that part, e power minus 0.4 minus e power minus 0.24, which is working out to this. The multiplication of these two numbers has to come out, which is working out to around 23.80. So the present value of this entire payment stream is working out to 23.806. So in this numerical, what are the things that we are going to understand? What if the payment stream is discrete, like 1000 received after 17 years? Or what if the payment stream is continuous? The extra thing that we'll get when it is continuous is one more layer of integration. One integration at the interest rate layer to arrive at the uniform, the discounting factor for the entire period. And the second integration at the amounts layer. The reason being, we are not receiving one-time payment. We are receiving a continuous stream of payments. That is where that one-time payment, whatever we have got, we have to integrate it to get a continuous stream of payments. So I mean there should be a little bit of more practice on this numerical, right? Where the force of interest is constant versus variable. If it is variable only, we'll get all these kind of difficulties. But there, at least the amount that is getting paid or received, you have to check out whether it is a constant one-time kind of a receipt, or a continuous kind of a receipt. In that case, it becomes more and more comfortable to solve these kind of questions. Probably we'll take a similar kind of an example, one more, to typically try out on a quicker note how do we operate in these kind of questions. All right, so let's look at one more example, especially the continuous stream of payment, so that we get some more clarity in terms of solving these kind of questions. Look at this. Now someone has given to us that the force of interest, again, it's a variable, saying between 0 to 20 years it is variable at the rate of 0.05 plus 0.001 t, more or less similar to the previous question, and above 20 years it is taken as a constant between as 0.05, around 5%. That's fair enough. Now what we are trying out is, we are saying that there is a continuous stream of payment that is coming in between t equal to 20 to 25, right? The continuous stream of payments are coming between this period, which is equivalent to this much of an amount. So I need to find out whatever is the accumulated value here. I am not looking at the present value. In this case, I am trying to find out the accumulated value, which is like a future value kind of stuff. But before we go into all that, first we have to work out on the interest rate part, because we have different kinds of interest rates for different kinds of period. So first let's find out the present value itself, and then we'll see the next part. So I'll say e power minus 0 to 20, 0.05 plus 0.001 s ds plus integral 20 to 25, right? This again I can put a minus instead of plus, 20 to 25.05 ds, which is working out to me e power minus 0.05 s plus 0.0005 s squared into s squared by 2. So that's where I have taken it as 0.0005 s squared integrated between 0 to 20, and also minus 0.05 s integrated between 25 to 20. So at least this part gets simplified to me as e power minus 0.05 into 20, which is 1, okay, 0.0005 into 20 squared, 400. So this works out to 0.2, right? 400 into 5 works out to 2000, so that I'll take it as 0.2, and this also works out as 0.05. So if at all I am talking about a t up to 25, right? Probably this, let me take it as a variable itself, because it may be for any period. So because I want to derive the interest rates in general, about 20 it is t, so I'll take it as t minus 20 into 0.05. All right. So simplification comes out to e power minus 1.2 minus 0.05 t plus 20 into 0.05 works out to 1. So this works out to e power minus of 0.2 plus 0.05 t. This could be the simplification for this interest rates. If I want my discount factor at any point, I'll take it as e power minus 0.2 plus 0.05 into t, as long as t is greater than 20. Right? If t is greater than 20, I will use this particular number as the discount factor. Now, so I'll take it as e power minus of zero point 0.2 plus 0.05t. So let me say, if at all this question had been to find out the present value, what would have been the case? I would have taken 30 into e power minus 0.015t. This is the amount that we are receiving in one single at a point in time. This I am discounting it with the discount factor, which is e power minus zero point 0.2 plus 0.05 into t. So overall this is working out to e power minus of 0.2 into e power, the t terms minus 0.015t plus 0.05t. 0.05 minus 0.015 working out to minus, so this is working out, both of them are coming out to minus itself. So this is working out to minus 0.065t. Am I right? Yeah, this is working out to minus 0.065t, and this entire thing has to be integrated between 20 to 25. So I can very well say minus 0.065t by minus 0.065. I'll take out even this part outside and integrate this between 25 to 20. Okay, so we can find out the values. 30 into e power minus 0.02, the same way we have done here. 30 into e power minus 0.2 divided by minus 0.065. This part works out to minus 377, and this becomes e power minus 0.065 into 25 minus e power minus 0.065 into 20. So this is actually working out to, yes, also this part I am omitting out, right? So e power minus 0.065, so e power minus 0.065 into 25 minus 20, which is 5. So this is working out e power minus point, no, this cannot be at an exponential level, right? Okay, e power minus 0.065 into 25 minus e power minus 0.065 into 20. This is working out to this much. So multiplication wise, I multiply these two, which will work out to 28.57 is the present value of this entire investment. All right. Yeah. This question was primarily asking for accumulated value instead of the present value. All you may have to do to find out the accumulated value is, here we have got that for the entire 25 years period, because he is asking for an accumulated value at t equal to 25. So you multiply that amount with the accumulation factor. What is the accumulation factor for us? E power 0.2 plus 0.05t, which will work out to e power 0.2 plus 0.05 into 25, which is 1.25, which works out to e power 1.45. This is what is the accumulation factor, which means you can multiply this number with e power 1.45 to arrive at the accumulated value. After 25 years, this particular amount, whatever you are going to receive, 30 into e power whatever, that particular stream of payments, whatever you are going to receive at the end of between 20 to 25 years, If at all I want to find out what is the current value of all that, I'll say it is 28.57. But if I want to find out what is the accumulated value at the end of 25 years, this is nothing but multiplying the present value by an accumulation factor of e power lambda t, and that lambda we have already worked out up for 25 years, or for anything greater than t greater than 20 years, what is that particular value. So that number I can very well use as a multiplying factor here to arrive at 121.81. All right. Okay. Moving on to the next numerical. Again the same scenario. The delta is treated as constant or a variable. Right, between 0 to 5 years we are saying that this is how the force of interest is going to change, and even above 5 years also this time it is not constant, it's another kind of a variable. So there are two different patterns, so which has nothing much for us to do, right? All we have to do is integrations over the period itself. Calculate the amount to which 1000 will have accumulated at t equal to 7 if it is invested at t equal to 3. So it's not going to be invested today, it's going to invest after 3 years, but I want to find out how much will it be after 7 years. So on this day we know that it is 1000. I need to find out what is the value on this particular date. Okay, logically what is that we have said earlier, the accumulation factor is nothing but e power delta t, and if at all delta is a variable, we said accumulation factor is e power t1 to t2 delta t dt. Correct. Now that for t1 to t2 it's not the same, because in our current example it should be e power 3 to 7 delta t dt, but we have two different deltas for two different periods. So that is where I'll break that 3 to 7 delta t dt into 3 to 5 as one aspect. So I'll take it as e to the power of, so in the numerator I'll put it 3 to 5 delta t. I'll take it as between 3 to 5. I know that it is 0.04 plus 0.003 s squared ds, and this I will break it as another part which is 5 to 7. I'll make it 0.01 plus 0.03 s ds. So just doing a quick integration, assuming now the concepts are getting sunk. 0.04 into 5 this s is becoming between 5 to 3. Similarly 0.003 into s cube by 3, which becomes 0.001 into s cube, which is being taken 0.04t, where you are integrating between 5 and 3, s cube you are integrating between 5 and 3, even 0.01 s, which you are integrating between 7 and 5, and even we are talking about 0.03 s squared by 2 into s squared, which we are integrating again between 7 and 5. Alright, so again as one more simplification giving me 0.04 into 5 minus 3, 0.04 into 2 working out to 0.08, 0.001 by 3, 0.001 already has taken that by 3, 0.001 into s cube, 5 cube minus 3 cube, 125 minus 27, 98 into 0.001 becomes 0.098, correct? Yes. 0.01 into 7 minus 5, which is 2, 0.02. Okay. And even the last one is becoming 0.003 by 2 into 7 squared minus 5 squared. 7 squared 49 minus 25 24. 24 by 2 it's 12. 12 into 0.03 becoming 0.36. So I have to add up these numbers. 0.08, right? You can look at the calculation part. Please don't make any mistakes. 0.08 plus 0.098 plus 0.02 plus 0.36. These are the various numbers that are coming up. So 0.558, and I take the e power of this, which will work out to 1.747. So the accumulation factor between 3 to 7 years going with this kind of a mechanism is 1.7471, which means if I am depositing 1000 at that point, it works out to 1000 into 1.7471, working out to 1747.1. This would be the accumulated value at the end of 7 years. So we have to be very careful in terms of doing these kind of calculations, which involve continuous compounding rates of interest. Now this we have already seen. Calculate the constant rate of discount per annum, convertible constant rate of discount per annum. We are not talking about interest. We are talking about the rate of discount, right? What is the formula for the effective rate of discount? We have said 1 minus D12 by 12, because we are talking of convertible monthly, to the power 12, whereas here this we are talking about as a 4-year kind of a period, right? So I'll take it as into 4. This is what I'm primarily looking at, whatever the return that has actually come out. So whatever the number that is coming out, which is this 1.7471, I'll take it as 1 minus D12 by 12 to the power 48. So if I do it to the power 1 by 48, it becomes 1 minus D12 by 12. Okay, this to the power of 1 by 48 is becoming 1 minus D12 by 12. So D12 by 12, oh sorry, this would be the interest rate, but I have to find out the discount rate, right? So this would be 1, this is if I'm talking about an interest rate, okay, 1 minus this, 1 minus D12 by 12 should be equal to this. No, this is not 1 minus D12 by 12, right? This is, I have to take 1 by of it, right? Because this value would be equivalent to, this is the discounting factor. This is a accumulation factor, right? In accumulating factor, what is that we said? E power lambda t, or this is even 1 plus I to the power t, or this may be equal to 1 minus d. So this 1 plus I to the power t is what is the return. So what is coming out for us is 1 plus I. So this is what has come out as 1 plus I for us. From this I can, so if we quickly look at it, we got the multiplication factor as 1.7471. Calculate the constant rate of discount per annum convertible monthly. 1 minus d12 by 12 to the power 12. This should be the nothing but the discount factor, V power n. But I need the accumulation factor, which is the reversal of this, which means I'll actually take it as 1 minus 1 by this to the power 48. So first let me find out the 1 by of that before I do this. So I'll do 1 by of this, which is 0.57. Then this becomes, if I do 1 minus d12 by 12 to the power 1 by 48. So this part, if I do this to the power of 1 by 48, it comes out to 0.98. This is 1 minus d12 by 12. So if I do 1 minus of this, this becomes d12 by 12. And if I multiply this by 12, this becomes 13.86%. For this entire period, if at all I want to find out the constant rate of interest, constant rate of discount compounded quarterly, I have to make sure that first I am accumulation factor, I am making it as a discounting factor by doing 1 by of it, because e power minus, see, this is e power lambda t, which is the accumulation factor, whereas e power minus lambda t is the discounting factor, which is so this has to become something like this. And after that I will go ahead with finding out the constant rate of discount or constant rate of interest or whatever is it as per the question requirement. All right. Okay, let's move on to our next question in this case. So in this numerical, we don't have a clear-cut value for lambda t. We are simply saying that it follows a plus bt for the entire period, which means it is still a variable. It is dependent on time t. It's still a variable following a plus bt, but we need to find out those a and b. What is it saying? Today, if you have deposited 45, it becomes 55 after 5 years. So what is the accumulation part? The accumulation is nothing but 55 by 45 is the accumulation part. And this should be equal to e power 0 to 5 a plus bs ds. This is the equality 1. Equality 2 will become 120 by 45 because it's becoming 120 at the end of 10 years. So this is becoming e power 0 to 10 a plus bs ds. Now if I simplify these two, you will get two different equations. So it is the first one, the integration is coming out to a into 5 plus b into s squared by 2, 25 by 2. So b into 25 by 2 is working out to 55 by 45. Similarly, the second expression is coming out to 10 a into 10 minus 0. I'm assuming that you are comfortable with the integration at this layer. S squared by 2. 10 squared by 2, which is 100 by 250 minus 0. So this is coming out to 50. This equal to 120 by 45. These are the two simultaneous equations in A and B, which I have to solve. 5a plus 12.5b is equal to 55 by 45. We can calculate using our calculators. 10a plus 50b is equal to 120 by 45. To solve this simultaneous equations, probably I'll multiply the first equation by 2, then I can use elimination. Alright, 10a plus 25b is equal to 110 by 45. So that is what is working out. If I'm doing a subtraction, it works out to 25b equal to 10 by 45. From where b comes out to 10 by 45 into 25. We can find out what is the value. So the value of b works out to, the value of b works out to 10 by 45 into 25. Alright, 10 by 45 into 25, which will give me B is 0.00. Am I right? Okay. 2A, yeah, 10 by 45 into 25 works out to be that particular number. Twenty-five B equal to 10 by 45. So 10 by 45 into 25 is the value of B, which works out to something like this. Now, if I want to find out what is the value of A, I can multiply this. I can use this expression 10A plus 50B equal to 120 by 45. What is the value of 120 by 45? This is the value of 120 by 45. All right. So 10A plus 50B is equal to that much, which will work out to 50B. This is B. So if I want 50B, this is this much. So 10A plus 50B equal to this much. So I can find out what is the value of 50B by doing a subtraction from this. Let me see if I have made any mistake here. E power 0.025 A plus, oh, sorry. Probably we have to do this numerical again because, oh no, T squared. So A plus 25 by 2 is 55 by 45. 10A plus 50B is equal to 120 by 45. So 5A plus 12.5B is equal to that much. 10A plus 50B is equal to this. So just taking the first case and then subtracting, giving me 25B equal to this. And from here, B has come out to that particular value, which will help me in trying to find out the value of A. 10A will work out to this minus this. This is the value of 10A. So from here, I can find out the value of A, which works out to this number divided by 10. So this is the value of A and this is the value of B. All right. We have made a mistake. Let's get back again. Right, the whole thing we did not take it as E power. Okay. So E power, putting it as 0 to 5, 0 to 5, A plus BS ds. This should be 55 by 45, but A plus BS ds integral is log of this. We ignored that part. So typically when I integrate this, it comes out as 5A plus B into S squared, which is 25 by 2, is not 55 by 45. It is log 55 by 45 because we are going ahead with the E power. This part we have missed out earlier, which means the second part will go as 10A plus B into 100 by 2, which is 50, is equal to log 120 by 45. So from here, the simplification is coming out. When I multiply the first one by 2, it comes out 10A plus 25B is equal to 2 into log 55 by 45. Now we will simplify this aspect. Log 120 by 45, if I am taking log 120 by 45, it's coming out to 0.90. Log 55 by 45, if I am doing, it's coming out to 0.20. and we are even multiplying it by 2 because 2 into log 55 by 45. Now I can subtract the 2, saying 25b equal to the difference between these two values. 25b is equal to the difference between the two values. How much is that 25b? 25b is this minus this. So from here I'll get b, which is this by 25, works out to my b value. So if this is my b value, I can find out a value very comfortably, right? 10a plus 50b equal to 0.98, which we got here. So probably I can do a 50b, which means this multiplied by 50. If I'm doing, I'm getting 50b. So 10a, if I want 10a, I am getting it as 0.98 minus this. So this is the value of 10a. From here, the a is working out as this number divided by 10, which works out to minus 0.017. So probably I can very well write this particular accumulation factor. In this case, the accumulation factor will come out as or probably the delta t. Delta t will come out as minus 0.01781 plus 0.02318 t. This is what will be the force of interest in this kind of an example. Now there is also a question that is coming out. Calculate the constant force of interest per annum if the accumulation is same from 0 to 10, which means 45. The accumulation factor for 10 years was nothing but 120 by 45. And this we are saying it should be equal to e power delta t, because we are talking of delta as a constant. I'll take it as 10 delta, straightforward. So 10 delta will be log 120 by 45, whatever this number. This is equal to 10 delta. So delta will directly be this number divided by 10, very straightforward calculation, which will come out to us as 9.81%. Right? So this is just a small corollary behind this problem, but otherwise the seriousness of the problem is the above one in terms of finding out the variables given a constant rate function, and the way the way people are going to accumulate money at different points in time. All right. Okay, now let's move on to our next example as a part of this. Similar kind of a problem which we have handled earlier, but the only scenario is we have three different kinds. Doesn't matter. I need to find out the present value of 1000 that is due to come at t equal to 10. So what is that that is going to work out for us? The 1000, logically speaking, it is nothing but the discounted factor is 1000 into e power minus of t1 to t2 delta t dt. This is what is the scenario. Now what we are saying, because our deltas are different for different periods, we are saying we'll add up all of them, we'll integrate all of them separately. From 0 to 5, this is going to be 0.04 plus 0.003 t square, or probably we'll take it s squared ds. Similarly, integral from 5 to 8, because we need 10 years scenario. Okay, but we'll take it as a variable again so that it can help us for the last question. Okay, so we'll take it for greater than 10. So 5 to 8 is also a constant for greater than 10. So we'll make it as 0.01 plus 0.03 s ds. Even this will come out as 8 to t 0.02 ds. So overall the integral will work out, assuming that you are comfortable with this basic layer of integration. I'll take it as e to the power 0.04 into 5 minus 0, which works out to 0.2, plus these all will come out with a tag of minus, right? All these are because we are talking about a discount factor, not an accumulation factor. So this will have a minus here, e power minus 0.2, 0.003 into s squared, 0.003 into 5 squared, no, 0.003 by 3 s square, so it becomes s cube by 3, so 0.001 into 5 cube, 125, so it becomes 0.125, plus 0.01 into 8 minus 5 becomes 0.03, plus 0.03 into s squared, so 8 squared minus 5 squared, so 0.03 by 2 into 64 minus 25, 39 by 2 into 0.03, and plus 0.02 into t minus 8. Right? So this is what the entire thing that comes under the minus. So if we simplify this, this is coming out to e minus 0.2 plus 0.125, 0.325 plus 0.03, 0.355, and this is nothing but 0.585, 355 plus 0.585, 0.94. So this is becoming e power minus 0.94 minus 0.02t plus 0.16. So overall it is coming out as e power minus 0.78 plus 0.02t. Probably the present value or the discounting factor in this case for this kind of a scenario is minus 0.08 plus 0.02t. We can use this number directly for this kind of a calculation also, just as a quick overview of what we have done, just as a quick revision to whatever we have done. So the same number I can put t equal to 10. If I put t equal to 10, it is working out to, this is minus 0.02t, okay, minus 0.02t. So if at all I am putting t equal to 10, it is becoming e power minus 0.98. So the discounting factor will be e power minus 0.98 into 1000, right? So whatever is the 1000 into e power minus 0.98. So which is working out to 375. So the discounting factor is nothing but the dis by 1000, which is 0.375, works out to be the discounting factor here. Now in this question, what is being asked? Calculate the constant rate of discount per annum convertible quarterly. So how do I convert it? As per quarterly, it is nothing but 1 minus d12 by 12, quarter, right? 1 minus d4 by 4 to the power 4 should be equal to that discount. But yeah, that is for a 10-year period. So probably this also I'll take it as 40. So 1 minus d4 by 4 to the power 40 is equal to this. So probably if I want 1 minus d4 by 4, I'll take it to the power 1 by 40. So this number to the power 1 by 40, this is 1 minus d4 by 4. So probably I'll do 1 minus this to get d4 by 4 and multiply this by 4 to get d4. So as per the constant rate kind of a scenario for this example, constant discount rate is working out to 9.68% in this case. All right. Now the next scenario, just which we have already done, probably you can practice it, or else I'm going to look at it. Calculate the present value at time equal to 0 of a continuous payment stream payable at the rate of 100 into e power 0.01t. Instead of 1000, we are making this number. But if I have to find out what is the interest rate, we have already got it, minus 0.78 minus 0.02t. So simplifying, it becomes 100 into e power minus 0.78 into e power 0.01t minus 0.02t, which is coming out to minus 0.01t itself. But this entire thing has to be integrated between 10 to 18, right? So probably if I simplify this integration, taking this part directly as a constant, e power minus 0.01 divided by minus 0.01, even that constant also, I'll take it here. So this works out to e power minus 0.01 into t. Again, this has to be integrated between 18 and 10. So let's simplify this number. 100 e power minus 0.78 divided by minus 0.01. 100 e power minus 0.78 divided by minus 0.01. This part is around minus 4584, and this side I can take it as e power minus 0.18, right? 18 into 0.01, yeah, e power minus 0.18 minus e power minus 0.1. So e power minus 0.18 minus e power minus 0.1, which is working out to minus 0.06. So if at all I want to find out the present value of all these, I am multiplying these two numbers, which is working out to 318. So the present value of all the stream of payments, which is doing at the rate of 100 e power 0.01t, is going to be somewhere around 318. So that is how we simplify these kind of numerical. So as far as this chapter is concerned, the major thing is trying to solve the numericals which are associated with the constant, the continuous rate of interest, the delta t, the force of interest kind of problem. Yeah, just to take one quick simple question. Nominal rate of discount per annum convertible quarterly is 8%. So what is the effective rate of interest on this? Right, nominal rate of discount convertible quarterly. So 1 minus D4 by 4. So D4 is actually 8%. So probably effective rate of discount, effective annual discount is what first I can try out. So 1 minus 2% to the power 4 will give me 1 minus D. From there I can find out total the effective annual discount first. Okay. Because it is given as nominal rate of discount is 8%. So D4 is given as 8%. So based on this, I can find out what is D, which is nothing but 0.98 to the power 4 is giving me 1 minus D. So 1 minus this is giving me D. D is the nominal, effective rate of discount. Now, we know that D, how am I getting the relationship? 1 minus D equal to V. So V, if I want, which is nothing but 1 minus D. Okay, 1 minus D is V. V is nothing but 1 by 1 plus I. So 1 plus I will become 1 by D. This is 1 plus I. And this number minus 1 will become I. So we have got our I, which is the annual rate of effective annual rate of interest. We have got our D, which is the effective annual discount. Now he is asking us to find out equivalent force of interest. So delta is what I have to find out. And we know delta is nothing but log 1 plus I. Right? Even log 1 minus d also we could have done. Minus log 1 minus d. Let's try that also. Minus log minus log 1 minus d. Even that will apply. Log 1 plus I will try. Log 1 plus I. This is this much. So 8.08. Or we'll say minus log 1 minus d. This is d. Even this is working out to be the same. So whether I find out I and then find out log 1 plus I, or directly find out minus log 1 minus d, it works out to be the same. The constant force of interest is around 8.08%. Calculate the equivalent effective rate of interest per annum, which we have already found out the I value 8.42%. Calculate the equivalent nominal rate of discount convertible monthly. Okay, so now I have to find out the nominal rate of discount convertible monthly, which means 1 minus d12 by 12 to the power 12. I need to find out this particular d12. So probably I can find out. We have already have 1 minus d. 1 minus d is already there with us. Right? This was our 1 minus d. So the moment we have our 1 minus d, probably to the power 1 by 12, if I do, I get 1 minus d12 by 12. Alright, so this I'll do it as this number to the power, right? So don't make mistakes, that's it. This number to the power 1 by 12 will become 1 minus d12 by 12. So if I do 1 minus of that, it becomes d12 by 12. So this is d12 by 12 multiplied by 12 becomes d12, which is the nominal rate of discount compounded quarterly, monthly. 8.05% is the nominal rate of discount compounded monthly. So convertible quarterly was 8%, but convertible monthly came out to 8.05%. Whereas convertible annually effective rate of discount was around 7.76%. All right. So I hope you are comfortable with at least some of these numericals corresponding to the interest rates. All these are quite comfortable. All these are quite relevant kind of a numericals that you have to look at, especially the things which will involve delta t. That's one major area you have to focus on for various applications in the areas of finance and insurance. If you have any further queries on this, feel free to get in touch with me on the number that I have provided below, or you can even send an email to me at vamsidhar@pacegurus.com explaining your question. Thanks a lot for listening to this session. Thank you very much.
Now let's look at comparing the effective annual rate of return of two different investments, or probably invested for two different time periods. If I want to compare which one has got a better return compared to the other one, how do I look at it? So how do I express both of them in terms of effective annual rate of return, and based on that do the comparisons. Look at this, a 90-day government bill was bought by an investor for a price of 96.1. So the purchase price was 96.1 per 100 nominal. After 34 days, the investor sold the bill to a second investor for a price of 97.75. So days, within this 34 days, 96.1 has become 97.75. And the second investor held the bill until maturity. So whatever for the second investor, it's as if he has purchased it at 97.75 and he has redeemed it at par on the maturity. So this is for 34 days, this is for 56 days. Now all I want to know is who has got the higher annual effective rate of return. So I have to convert both of them into annual effective rate of return, and based on that do the comparison. So it's as good as saying 96 for the first person, 96.1 multiplied by 1 plus I1. Now this is for 34 days only. So what I can do, over to the power of 34 by 365. This is equal to 97.75. From here I can compute I1. So 1 plus I1 to the power 34 by 365 is equal to 97.75 divided by 96.1. Now this entire thing, if I raise it to the power 365 by 34, this would become 1 plus I, and if I subtract minus 1 from it, if I subtract 1 from it, I get whatever is the value of I1, which is the annualized interest rate corresponding to the first party. So all I can try finding out is 97.75 minus 96.1. Sorry, it's not minus, right? Divided by 97.75 divided by 96.1 raised to the power 365 by 34 minus 1. So this is around 20.52%. So this particular 20.05% is the annualized rate of return in this particular investment. Now probably the same logic I can apply to the person 2, the investor 2 who has purchased it at 97.75. I'll say into 1 plus I2 to the power. He held it for the remaining 56 days. 56 by 365 is equal to 100. So from here I can get I2 has 100 divided by 97.75 raised to the power 365 by 56 minus 1. This is what will be the I2. So this comes out to 100 divided by 97.75. This is for that holding period, but if I want it annualized, I will do it as 365 by 56 minus 1. So this is working out only to around 16%. So the second investor is getting only 15.99% annualized, whereas the first person is getting 20.05%. So obviously our answer will go for first investor, who is getting around 20% profit out of the investment. So whenever we have to compare two different investments, it's always better to compare it on the effective annual return basis. because if we see in the first case, the actual returns, only the periodic returns, if we see, the first person 97.75 divided by 96.1, around 1.7%, right? If I subtract 1 from it, it comes to 1.71 or 1.72%. That was the holding period return for the first person. Whereas for the second person, 100 divided by 97.75 minus 1, if I am doing, it is coming out to almost 2.3%. So it would have given us an indication that the second person is more profitable compared to the first person. So, the second person's 2.3 was over a 56-day period, whereas the first person's 1.72 was only over a 34-day period. So that's the reason even the time periods wise the dates have to match, the comparisons have to match. So that's the reason we look out for effective annual rate of return for the comparison purposes. So on those grounds, we can very clearly say that the first investor has got a better return compared to the second one. Alright. Now, how do I look at converting between the various effective rates of return? Right? Converting between the various effective rates of return. We have seen earlier that the relationship like 1 plus I, where I is the annual effective rate, should be equal to 1 plus I semi-annual by 2 whole squared, or the same should be equal to 1 plus I quarterly by 4 to the power 4, and similarly 1 plus I monthly by 12 to the power 12. All of them should be equal, and again I is related with the D, right? So instead of I can very well write D equal to IV, right? D equal to IV. So instead of I could very well express D. So probably the other way of writing it is I by 1 plus I. So probably if the whole of I have to write it in the form of D. D equal to 1 1 minus D is equal to V, right? 1 minus D equal to V, which is 1 by 1 plus I. So even from that logic I can very well link up my I and D, right? So the equation across, if we see here, an investor is considering two or probably from a D standpoint, again we have 1 by D annual, 1 minus D annual should be equal to 1 minus D semi-annual by 2 whole squared equal to 1 minus D quarterly by 4 to the power 4, and should be equal to 1 minus D monthly by 12 to the power 12. So again the same kind of a logic exhibits in terms of D also. So if I am taking this particular numerical, considering two investments, one is a 4 monthly deposit which pays a return of 7.3% convertible half yearly. This 4.3%, 4-month deposit pays a return of 7.3% convertible half yearly. So what is the effective rate of return that is paid, effective annual return that is coming out of the deposit? Because this is a semi-annual, I'll take it as 1 plus 7.3% by 2 to the power 2 minus 1. That is what is the semi-annual deposit. So I will take it as 1 plus 7.3% by 2 to the power 2 minus 1. So it's around 7.43%. 7.43% is, so the first one is working out to 7.43% per annum. That is the effective annual rate of return in this case. The second is a 3-month government bill. What we have to understand is the government bill goes with a simple rate of discount, right? The government bill goes with a simple rate of discount. So, if I assume that some X percent is that simple rate of discount, so typically the amount that is paid on the government bill, or probably the D is what the government bill typically goes with. So now that we have got the I as 7.43%, I am interested in trying to find out this particular D, because the effective annual rate of return for both of them is the same. So, and that too because it is convertible on a quarterly basis. All I require is 1 minus d4 by 4 to the power 4. This, so once I compute the d, I am actually interested in finding out this d4. That, so the equation should happen at, from the I will try to find out the d, and from the d I will try to find out the d4. So how do I get d from I? D is nothing but I by 1 plus I. So using that formula, I will compute the D. So saying I divided by 1 plus I will give me D, and 1 minus D, that is equal to 1 minus this much. So 1 minus D is same as 1 minus D4 by 4 to the power 4. So 1 minus D4 by 4. So just doing this, 1 minus d4 by 4, this goes to the power 1 by 4. This is 1 minus d4 by 4. So from here I will find d4 by 4 as 1 minus of this. This is my d4 by 4, and from here I will get my d4, which comes out when I multiply this by 4, saying it is around 7.1%. So 7.1% is that rate of discount. If you try out, when you are having a effective rate of discount of D4 of 7.1, or probably when I put for one more, it is 7.11%. So when the discount is 7.11%, all the person would be paying is 7.11% by 4 into whatever is the amount to get. So to get 1, he will be paying 1 minus 7.11% by 4, and that would lead to an annual rate of effective rate of return of 7.43%. So we should get that comfort level in doing the conversions between the I's effective rate of interest and the D's, the rate of discounts. All these linkages should come quite comfortable to really price the securities, or try to find out the value of the various investments which are priced differently on different forms. All right. Now let's look out for the conversions between the various interest rates as well as discount rates. Probably once I know the interest rates, how can I compute the discount rate, or vice versa? So let's start looking at a couple of numericals like this. But before we look at it, I think I want to quickly revise the formula underlying this. The interest rates we are denoting by E, whereas the discount rate we are denoting by the letter D. And an annual effective interest rate is I. So this should be equivalent to semi-annual, right? This is the semi-annual compounded interest rate, nominal interest rate convertible semi-annually I2. This should be same as nominal interest rate convertible quarterly raised to the power 4. Similarly, this should be equal to the nominal interest rate convertible monthly to the power 12. The same way in case of D also, annual rate of discount is D. We have discount rate convertible semi-annually, nominal rate of discount convertible semi-annually. This should be same as nominal rate of discount convertible quarterly to the power 4, and same thing 1 minus D12. D12 is the nominal rate of discount convertible monthly. So all these relationships are the same, and on the other side we have a relationship D equal to IV. V is nothing but 1 by 1 plus I. So the other way I can write D is I by 1 plus I. Probably this can also get written as 1 minus V. So D is 1 minus V, or D is IV, or D is I by I plus 1. All these relationships still hold true. So the moment I am given one particular rate, I should be able to convert it into other using these kind of mechanisms. Alright. So let's look at the numerical so that we can try solving these questions. The nominal rate of discount per annum convertible quarterly is 10%. So it is given D4 is 10%. Right? Calculate the equivalent force of interest. Force of interest is delta. So even if I get I from it, log 1 plus I is nothing but delta. So first of all, let's go for a D. So D4 is 10%. So 1 minus D4 by 4 to the power 4, this should be equal to 1 minus D, right? So from here I can get my D. So now that D4, now that D4 is given as 10%, we can take it as 1 minus D4 by 4 to the power 4. That will give me 1 minus D. So I'll take 1 minus D4 by 4 to the power 4. This is 1 minus D. From here I'll get my D. I'll get my D as 1 minus of 1 minus D. So this is the value of D. And from here I can get my I, because D equal to I by 1 plus I, or D equal to 1 minus V. So V equal to 1 minus D. So V equal to 1 minus D. This is the value of V. V is nothing but 1 by 1 plus I. So from here I can get 1 plus I equal to 1 by V. So this is 1 plus I. So from here I am going to get my I as this minus 1. So in this case I have my I as this much. Now I can find out delta log 1 plus I, which is the equivalent force of interest, log 1 plus I. So even if I have got 1 plus I there, I can start from there itself. So the equivalent force of interest corresponding to a discount rate of 10% is 10.13%. So I mean there could be an intermediate formula, but if I am going from the basics, There is no way I can make any kind of a mistake on the same. Now, calculate the equivalent effective rate of interest per annum, which is I. I we have already computed, which is 10.66%. Let's say. Let's look at 10.66% is the value of I. Calculate equivalent nominal rate of discount per annum, convertible monthly and convertible semi-annually. All it is asking for is D12 and even D2. Same logic I can use. 1 minus D is already known. So I can say 1 minus equal to 1 minus D12 by 12 to the power 12. So from here, if I do 1 minus D to the power 1 by 12, that is what I will get as 1 minus D12 by 12. So D12 by 12 becomes 1 minus of this and 12 times. So 12 times 1 minus of 1 minus D to the power 1 by 12 is what is my D12. So I can try finding out D12 from here, which is nothing but 12 times 1 minus 1 minus D to the power 1 by 12. What is 1 minus D? I have this 1 minus D to the power 1 by 12. So this is coming out to some 10.08%. The semi-annual discount is coming out. See, the effective annual rate of discount is 9.63. The monthly is 10.08. The quarterly is 10, and probably semi-annual should be between 10 and 9.63. So this is 2 times 1 minus 1 minus D to the power half. This is around 9.875%. So that is how we are seeing that the annual discount rate, right? If it is a nominal discount, convertible semi-annually it is 9.88, convertible quarterly it is 10, convertible monthly it is 10.08%. So that's how we can try looking at conversion from one form to other. The moment I have a clarity on the equation, all these kind of numericals can quite comfortably be resolved. Look at one more aspect here. Calculate the nominal rate of discount per annum convertible half yearly, which is equivalent to. So D2 is what I want to find out, or probably we will write it in a better notation. This is D2. Nominal rate of discount per annum convertible half yearly. This is what I have to find out. Effective rate of discount of 2.25 per quarter. So the effective rate of discount for the quarter is 2.25. So from here all I can find out is the discount per year, which comes out as I can find out first 1 minus D to the power 4 is what is my 1 minus D. Probably this is a quarterly discount. It's not a nominal rate of discount. So directly I am taking, this is effective rate of discount per quarter. So if I take it to the power 4, it becomes effective rate of discount per year. So probably D, let me call this as per quarter. Effective rate of discount per quarter 2.25%. So from here I can get my D, which is nothing but 1 minus D, which is nothing but 1 minus 2.25% to the power 4. This will give me 1 minus D, and probably from here I can get my D also. So the D in this example is 8.7%. Okay. But what D is required is D2, convertible half yearly. So I require D2. As we have said, 1 minus D is equal to 1 minus D2 by 2 to the power 2. So if I start taking this as half, this will not exist. 1 minus, this will not exist. 2 into, this will not exist. So D2 becomes 2 into 1 minus this. So if I want to find out D2, it's nothing but 2 multiplied by 1 minus 1 minus D to the power half. So around 8.89%, 8.9% happens to be my D2. Now look at another thing. A nominal rate of discount of 5%, convertible every 2 years. It's not convertible every half year or something, which means this is D half. Same logic. D half is being given as 5%. So again 1 minus D is equal to 1 minus D half by half to the power half. Right? 1 minus D2 by 2 to the power 2. 1 minus D half by half to the power half. So 1 minus D will come out as 1 minus of D half is 5% by half to the power half. So 1 minus D. So we'll say D half is 5%. So from here I'll get my 1 minus D as 1 minus 1 minus D half by half to the power half. This is what comes out as 1 minus D. So from here comes my D as 1 minus this. But all I require is D2 again. D2 is equal to 2 times 1 minus of 1 minus D to the power 1 minus of 1 minus D to the power half. This is what is D2. So D2 works out to around 5.2%. D2 works out to 5.2%. So that is how we can very well consider the conversions between the various interest rates and the discount rate. All we need to have is the clarity on the usage of the formula and the interaction between the various interest rates and discount rates. Alright.